Okay, so let me start. So I'm actually pretty happy to do one of these speaker corner. I mean, I've heard about it. I even registered to it. But okay, it's the first time I do one. So I want to discuss today a problem that is very, very close to my heart. And that's essentially the problem of how we can take into account correlations in computational quantum transport. I mean, I've been doing quantum transport for a long time already, and we have been doing tons of very nice things. But there are some problems that are very, very important in the physics, I mean, the actual device. And very frustratingly, we have, it's very difficult to tackle them. And so I want to discuss today our take to try to address this problem. So more specifically, I'm involved in a project called QUANT. I mean, many people in the audience come from a Anton group, so you know about QUANT. It's developed in Grenoble and in QDEFT. And essentially QUANT, okay, I think it may be a bit, maybe I stripe it really to the bone when I say that, but essentially it solves quadratic problems like that for a large class of Hamiltonian that you can write essentially as quadratic Hamiltonian, so non-interacting problems. And we cannot do all of them, but we can do many problems like that, and many important problems like that. Recently, we have been essentially trying to extend QUANT to do also time-dependent problem, TQuant. So now TQuant is also an open source project. You can download it. And essentially, it's the same as QUANT, and actually it uses a lot of QUANT things. And then you can send the voltage pulse and see what kind of plasmon it generates in your Fermi sphere and how it propagates, and then maybe in an interferometer or maybe in a topological material or something like that. And that's very nice, and it works fine. And so the problem I want to discuss today is what if you have electron-electron interaction? So now you have terms that are not only quadratic, but are quartic, so interaction terms. And of course, this is a tough problem. We know it's tough. And so there are, many people have spent their lives to try to solve this. So I'm not claiming that we are going to solve that in the greatest generality, but I will show you one path which is very nice in the sense that it is somehow a direct, I would say, natural prolongation of QUANT and TQuant, where we can do a lot of things, and I think we will be able to do even more in the very close future. So why is it an important problem? Once again, you just take a quantum dot, which is the main example I will focus on today, which means you make a small puddle of electrons, and coupled maybe to two reservoirs so that you can actually do some quantum transport through it. And even this very simple problem, which is what most people for example, who tries to build a quantum computer are essentially dealing with this system. And you get Coulomb blockade. And Coulomb blockade already, it's very frustrating. It's a very simple problem, Coulomb blockade. We understand all the physics, but how to integrate Coulomb blockade inside something like QUANT, I don't know how to do it. At least I don't know how easy to do it. And then if you increase the coupling between your quantum dot on the leads, and you have genuinely interacting physics, like the Kondo cloud that can form, for instance, along the things. And this is really true non-interacting physics. And we would like also to be able to do these things. And then there are a long list of things in nanoelectronics, like the 0.7 anomaly, or device in the fractional quantum effect, or even quantum computers, because at the end of the day, a quantum computer is a many-body system that you control very well. So a long list of systems that we would like to be able to address, not to mention correlated materials, which is another big class of problems with interactions. So we are motivated to do that. Essentially, so I'm going to say a few words about QUANT on TQuant, I mean very few, and then I'm going to tell you how we are going to try to tackle that. So QUANT and TQuant, just a gallery actually, just to say that these quadratic problems, they are simple enough that you can, with one program, you can do a lot of different situations, like graphene or quantum Hall effect, or like these are spintronic materials or topological insulators. I mean, tons of different things can be done with one program. And if you think about correlations, most people in correlated physics are taking a very boring non-interacting problem. Very boring non-interacting problem, just I don't know, like 2D plane, for instance, Hubbard model, like a 2D plane with a lattice. And then all the interesting parts come from interactions. And in quant, it's more or less the opposite. We start from interesting non-interacting problems. So now the question is whether if we start with something interesting already at the non-interacting problem, maybe by just putting a little bit of interaction, we will be able to do something new and something interesting. So this is quant. T-quant is just about the same, but for time-dependent problems. So you can do, that includes, for instance, Josephson effect. If you put a bias across a Josephson junction, then you have AC Josephson effect. So this we can do with T-quant. For instance, if you can see the multiple Andreev reflection across a Josephson junction. You can send pulse. For instance, this is a pulse in a quantum Hall effect. You see your pulse propagates along the edge state here. So there is an edge state like that. And then you can actually ground this gate here. This dashed red is a gate. You ground it, and you have no more edge state. I mean, now the edge state is here. And so you see your pulse is stuck in the middle, and you can now put the gate again, and then it will restart. Or you can put the other gate in front, and then it will restart, but in another direction. So this kind of game that we can play with T-quant, for instance. So that's enough about these non-interacting things. And now let me jump into what we want to do. And so we are going to have a very, very simple and very, very crude approach to the problem. Essentially, we are going to do perturbation theory. That's essentially the only thing I know how to do with an interacting problem. So we have an non-interacting problem that we treat with quant, let's say. And then we want to expand in power of the interacting Hamiltonian. And we want to calculate something, an observable, for instance, or a green function, in power of u. Essentially, that's what we are going to do. So this problem breaks down into 3 sub-problems. First, we need to calculate these coefficients. Okay, that's the first problem. It's not totally trivial. And then I will show you how we do that. I mean, that was already 5 years ago that we found an ID. And the main problem is that when you, this can be, this perturbative theory that can be put in terms of Feynman diagrams, and there are a large number of them, factorial n of them, so that's big. And so 5 years ago, we found an idea to go from factorial n to 2 to the power n. And 2 to the power n is something that we can deal with. 2 to the power 10 is 1000. So typically now we can calculate 10, 15 orders of perturbation theory. This is what I'm going to show you. Like we can get with some precision, a few digits, 15 first orders of perturbation theory. So yeah, first problem is how to bring down the number of diagrams. Second problem is that now these diagrams are essentially n-dimensional integrals. So how do we do these integrals? And I will explain also how we switched gear there. Initially, we were doing just Monte Carlo sampling. So the whole field is known as dramatic Monte Carlo. And now we are not doing Monte Carlo anymore. So I will tell you a bit about how we calculate these integrals. And then the last bit is also interesting, is suppose I give you the first 15 coefficients of this expansion of the right-hand side. How do you reconstruct the left-hand side? And I will show you how we use conformal transformation to do this reconstruction, and how you can go significantly beyond the radius of convergence of the initial series and get non-perturbative results. But before I do that, let me introduce a bit the example I will focus on. And also I will show you some teasers, some results that you are to convince you to stay until the end of the seminar. So I'm going to focus everything I say on the Anderson impurity, on the out of equilibrium Anderson impurity. So we will be able to put a bias voltage. So essentially you have a quantum dot here with 2 reservoirs, and we model that with just one interacting side here, with hopping here, which is small, that connect to the rest of the leads, so the left lead and the right lead. So that's the Hamiltonian. So hopping terms, this gamma I is essentially 1, except between the quantum dot on the leads. And you have some gate voltage here that allows you to tune the potential at this quantum dot. It corresponds to the gate voltage you can apply to this central gate, for instance. And you have the interaction. So you pay a price U when you have 2 electrons sitting on the central side. And we essentially, in the formalism, we switch on this interaction at time equals 0. Then we wait until we reach stationary regime where we have the interaction problem that we are interested in. So that's the out of equilibrium under some impurity. It's interesting and it's relevant for physics. So first there is Coulomb blockade in it. Coulomb blockade. So to understand Coulomb blockade, you just look at the energy of your system if it is totally decoupled, and you find that it's okay. That's you can solve it. It's trivial. So you have the n square term on the n term. With n is the number of electrons. And so it takes some energy usually to put another electron in your system because of Coulomb interaction, unless you are at some special point where the energy here of n+1 on n is equal, and then you can really easily tunnel in the system. So this is something that has been observed thousands of times. Typically, this is okay. I took one example from my friends, but I mean there are tons of those. Although those are particularly nice. So this is a Coulomb diamond as a function of the gate voltage, so what was called epsilon d in the model, on the bias voltage across your system. So you see these points here at the degeneracy point where n and n+1 electrons have the same energy. So here we can tunnel, and you cannot tunnel in between. It's Coulomb blockade. So that's the first effect that we have in this Anderson model. And the second is Kondo effect, which is much more interesting effect. So let me give you my one slide understanding of what is Kondo effect. So you have this repulsive interaction, so you don't want to have two electrons on the side. So now suppose that the U is huge, but not infinite. It's big, but not so big. Now you have an electron, you have a single electron here. Let's say it's pointing down. And now you consider an electron from the reservoir. So if the electron is down, it cannot simply not go there. It can, because of Pauli principle. So if the electron is down, it cannot go there. But if it is up, it can go there with a very small amplitude, and essentially that's gamma square, so the hopping square divided by U. That's just second order perturbation theory. And that means that you gain a little bit of energy by being antifermatically coupled with this electron. So you start from a repulsive interaction, and effectively you get antifermatic coupling. But now if you think about it, you get this antifermatic coupling only if the electron is close to the quantum dot, which means that this interaction is also an attractive interaction. So at the end of the day, you started from repulsive, and you get an effective attractive magnetic interaction that's going to bring you some cloud, which is called the Kondo cloud. So you have an increased density of state at the Fermi level of electrons that are trying to screen the spin of your impurity. That's a Kondo effect in one slide. By the way, I didn't say, but if you want to stop me to ask any question during the talk, please do it. I mean, it's always better not to be speaking in front of a screen. So if I get some feedback, I'm happy. Plus, if I can help to clarify something, I'm also doubly happy. So that's Kondo effect. And it's also been measured tons of times. So you need to tune a little bit more your quantum dot to see it. You need essentially to be slightly coupled. If you're too much decoupled, you don't see it. The Kondo temperature is too small. But if you increase a little bit the coupling to your reservoirs, you get this nice so increase of transmission. Transmission only when you have an odd number of electrons inside the system. So you see this is your Coulomb diamond, and in between, before it was just zero current, but now we have a nice Kondo, which is called the Kondo ridge. Then nothing when you have an even number of electrons, because and then another Kondo ridge. On the principle, you could have several like that in a row. So that's the Kondo effect. And so now is my teaser. This is a result of a calculation that we can do. It's actually just a single run of the code. It's actually the density of state on the impurity, so the local density of state, or the spectral function, as a function of frequency. So 0 is the Fermi level, and as a function of interaction. And you see, initially at 0 interaction, you get some resonance, which is slightly offset from the Fermi level because we have put some epsilon d, some voltage, gate voltage here. And as we switch on interaction, it gets narrower and narrower. So you get here this Kondo resonance. And also, it gets pinned to the Fermi level. So you see, it was slightly offset, and now it's exactly at the Fermi level, or almost exactly at the Fermi level. And you also have these side bands that are called the Hubbard bands that correspond to doubly occupied quantum dot or 0 electron of the quantum dot that show up on the side. So what is nice about this calculation is that we could get that in just a single run, the entire frequency and interaction dependence in one run. But this is something that you could obtain with other techniques like NRG, for instance. So it's not in itself enough to claim that you have a wonderful new tool. But we have one success story. There is one problem that we solve with this technique, which, as far as I know, cannot be solved, or at least not as well with any other technique. And that's the same thing, but now we put the bias voltage again across the impurities. So now it's out of equilibrium and some impurity. And here it is. And so now you see you have, okay, this time there was no epsilon d, so it was the resonance, initial resonance was at the Fermi level. And when you switch on interaction, it gets narrower and narrower. And you also see the side bands, about bands. But at some point, you see the bias here. You see the two peaks corresponding to the bias voltage in between your two electrodes. So what's going on essentially there is that essentially you have two Fermi levels now because you have a bias. So you have the left electrode and the right electrode. So your system wants to make a Kondo resonance with both Fermi levels. That's why you will get two peaks. But at the same time, bias is working a bit like a temperature, so it's trying to kill the Kondo effect altogether. So so the system, the thing goes down to any. And so the question that was the point was actually whether you can see the splitting before you actually have killed everything or not. And it was not actually clear, and it was like several contradictory paper. But actually now we can have an exact result for this, and we can see that actually we have nice regimes like this where we see the splitting. So it's a teaser. So essentially, in the rest of the talk, I will be just talking technicalities. I mean, explaining you what is the route to get this nice plot that we developed. So the first problem, once again, is to calculate this diagram. On really the bare output of this diagrammatic approach is we calculate order by order things. For instance, this is the self-energy, a function of frequency for order 2. Order 4, order 6, order 8, and order 10. Real part and imaginary part. And you see here at order 2, you get something fairly big, I mean 10 to minus 2, and then it goes down to minus 10 to minus 4, so it's decreased, and but we still have a reasonably good accuracy. So those calculations are actually were already a long time ago. Now we have much better techniques, so probably if we redo them, it will be much better. So let me introduce KELDYSH formalism in just one slide, because I will be using it it's something that's very often people are a bit scared by KELDYSH, and it's actually very simple, much simpler than it sounds. And so essentially what we will do, we start at t equals 0 from a non-interacting problem. And that's good, because non-interacting problem, we have QUANT, we have t-QUANT, so we know how to solve them. And then at t equals 0, we switch on interaction, u of t. So this is u is actually the evolution operator due to interaction, so in interaction representation. So we switch on interaction. Then we measure whatever it is that we want to measure, the observable. And then, actually, that's where KELDYSH is a bit different from what you do in a usual field theory. So in usual field theory, you will continue all the way to infinity, and then you will be annoyed because then you can pick up a phase and you have to divide by this phase, and so there is all these things that how you have disconnected diagrams and all these things that appear. In KELDYSH, you do something much simpler. You measure and then you go back to the non-interacting. So you just go back in time to your non-interacting state that you had at t equals 0. So advantage is that conceptually it's much simpler than other approaches. Disadvantage is that when we are going to do perturbation theory, which means that we are going to expand the evolution operator in power of h int, now you have terms that can go before I measure or after I measure. So two kinds of terms. And we have to keep track of whether they are, when you have in the expansion, they come before or after the time where I observe this. So this is known as the KELDYSH contour, and usually it looks like a slightly obscure mythical object, maybe on the complex plane. And actually, it's a very, very simple thing. It's like, so this is a KELDYSH contour, the way you will see it on any textbook. there are but essentially there are two branches, and these two branches just mean my h int, my interaction Hamiltonian, did it come from a term before or after the time t where I'm going to measure? That's it. So essentially, for each time, we have another index which takes 0 and 1, which tell me whether it comes from a term which was before or after O in the perturbation. And that's it, really. There is nothing more to that. So in terms of practicalities, when you do KELDYSH, you have to carry this KELDYSH index, 0 and 1, which makes things more complicated if you do things by hand. But on the other hand, if you want to teach your computer how to calculate Feynman diagrams, it's actually much simpler. Because this bookkeeping, the computer can do very easily. So we do this expansion in power of interaction, and then we get to calculate, average of product of C dagger C's, essentially like this, and then we do the only thing we know how to do, which is we use WICK theorem, and so this essentially is the sum of all permutation of C dagger 1, P of 1, where P is a permutation of 1, and so on and so forth. That's the WICK theorem, the way we learned it. Times the -1 to the power of the sign of this permutation. And usually, if you do field theory, you will look at these terms, and one by one, you will make a drawing corresponding to each of these factorial n terms, and each of them is a Feynman diagram. And that's not what we are going to do here. It's very nice for doing analytics, but for numerics, actually, you have much simpler things that you can do. You just recognize that this formula here is just a definition of determinant of this matrix, C dagger I, Cj. And if you stare at it for 10 seconds, you will just find that, yeah, this is actually the textbook definition of a determinant. And determinant is much faster to compute than factorial n terms, because you can compute it in n to the cube. So that's very nice, and that's what we are going to do. But there is a caveat that if you do that, you get all diagrams, including the disconnected ones. And the disconnected ones are terrible because they can actually, the integral later, they don't converge very nicely. You can have 2 times that go away, and your integrand doesn't go, doesn't converge. So we need another trick. And the trick is actually very simple. The trick is to perform exactly the sum over KELDYSH index, this KELDYSH index that I introduced previously. So if you do exactly the sum over KELDYSH indices, which means that now you have 2 to the n of them, because there are n KELDYSH indices, if you want to calculate to power n, then you get a nicely behaved integrand that you can have a chance to calculate the integral. So at the end of the day, we get this very simple formula, which is very ugly. It's both very ugly and very simple. So on the left is what we want: observables, green functions. It's essentially the green functions of the contour, KELDYSH contour. And on the right, you have a multidimensional integral, sum over KELDYSH, okay, maybe sum over vertices, of determinant of non-interacting green functions. And so essentially on the right, we have stuff that we know. These non-interacting green functions, we have, for instance, an explicit formula that relates them to the wave function that we get out of QUANT. This psi of alpha e, actually, this one we get out of TQuant, but we also have the one for stationary problem from QUANT. So this is a direct output of QUANT. So we just calculate the non-interacting green function, okay, just an integral to do. And then it's determinant of guys that we know how to calculate. So in principle, we should be able to calculate order by order this diagrammatic. So that's essentially the idea. It's very simple.
Xavier?
Yes.
If I may, so first of all, I wanted to check if I understand things correctly. Is there a clear reason or a physical intuition behind the constellation of disconnected diagrams if you perform summation of KELDYSH indices?
Physically, no. I mean, at least not that I'm aware. And actually, something that we discovered, and that's really what triggered this project initially, was the fact that not only the disconnected diagrams cancel, but they also cancel at the level of the integrand. So before you do the integration. And that's why that's why you have a very well behaved. I can prove it. I mean, the proof is in. We will put it in the paper. But honestly, no, I don't have a physical intuition for that. It's really technical. On the other hand, it has to, I mean, at least at the level of the integral, it has to, because we know that they disappear from the physically. I mean, this we know. That would be physically incorrect to have, you know, things that are not connected to what you are doing, that playing in a role. But the fact that it happens at the level of integrand already was something very important on the. Yeah. And so it was really the technical point that really triggered all this project.
So also related to this, to the statement about the integrand, I guess it means that in practice you interchange the summation and the integration in the formula, right? So
exactly.
Yes.
Exactly.
Ah, okay.
Yeah. Yeah. It should
and
should...
Yeah.
Yeah.
Finally, also one last question about this formula. So here you are evaluating a single particle Green's function. Is that right?
Yes, but if you want to add a two particle Green function, then you just add one row and one column to this determinant.
With the external indices.
With external indices, yes.
All right, got it.
I will show in a couple of slides how you can get, because if you just take this formula the way it is, for one run, you just get a single value of t and t prime. But we have actually nice tricks by expanding this formula, for instance, around the last row, you get the entire frequency dependence in just a single run, or time dependence.
All right, very nice, thanks.
So yes, about this sum of KELDYSH indices. If you just take, for instance, at order 4, the integrand as function of these two times, u1 and u2. For the 4 different KELDYSH index, you see these 4 panels on this integrand, and you know it does not decay when time becomes large, and also you see that blue is positive and red is negative, so this is going to be mostly cancelled by that. And so if you want to do the integral there, it's a nightmare. But if you do explicitly the sum over A1 and A2, you get something there that is very well behaved. Now it's concentrated in a small pocket close to time equal 1010, which is where we are measuring here. Also, I didn't put the scale, but here this is actually almost 10 times smaller than this. So you get you get the structure. So this we can have a chance to calculate. This I would not know how to do that. Some people tried and they got terrible results. Okay, so I think we solved. I mean, we solved the. I know this is what I mentioned. You can, if you expand the determinant against the last row, you essentially get some, you know, over, for instance, this times the determinant, where you just remove this row and this column, and now you see that there is no time t in the remaining determinant, which means that you get the entire t dependence by calculating these n terms. And that's a trick that we use if we want to calculate the full Green function in single run. And okay, so essentially we have solved the first problem, which is how to get nice integrands that we behave well. Now we need to calculate the integral itself. That's the second problem. And also, essentially, we want to do an n-dimensional integral. And if you have done the integral numerically in your life, you know that dimension 1 is easy, dimension 2 is okay, and dimension 3 start to be a pain in the neck. And very soon, it's almost impossible to do it with regular quadrature method. And most people switch directly to Monte Carlo calculation using, for instance, most well-known algorithm is Metropolis. And Metropolis is nice, and this is what we did in Chile, actually, in the first few papers. But it has a very slow convergence. So if you have n points in your calculation, your convergence is at 1 over square root of n. That means that if you want to add a new digit to your system, you need 100 more points. That's a pain in the neck. Compared to 1D, where you get essentially exponential convergence, or very fast convergence at least. And so, some time ago, we realized that we needed actually billions of function calls to actually get the integrand. And each time we were using this Metropolis, Monte Carlo, which is actually what is known as Markov chain Monte Carlo. And by Markov chain, you have the idea that each point is new and ignore all the points that you know before. So essentially, we are building no knowledge on this function. And that's a pity, because we have a billion points. We have a billion points of this function, so maybe we could learn a bit something about it. So we have this idea of starting to use some sort of machine learning to try to see if we could not build an approximation of the integrand that would help us maybe to do the Monte Carlo, for instance. That's an idea that we had initially. Now it has moved a lot. We are very far from this idea now, but that was the initial idea. Let me just say one word about why it is tough to calculate high-dimensional integrals. It's known as a dimensional curse. I mean, suppose that you have a function that is essentially 1 on a small part of your line, and then almost 0 there. If you just throw points there, very few will actually be in the region of interest. But I mean, if it is in 1D, it's okay. But if you do it in 2D, already you get very few square points. That starts to be a pain. And in 3D, it's very few to the cube points. And so at the end of the day, it's known as a dimensionality curse. Is that if you try to put points evenly on the cube, and you have this problem that the integrand is concentrated in a small pocket, so the number of relevant points scales exponentially bad with the dimension. This is known as a dimensionality curse, and this is why you need some sort of what is known as important sampling, so some method that put points automatically in the region of interest of your integral. And that's what Metropolis does for you. And I'm not going to discuss Metropolis today. I'm going to discuss what we did instead afterward. And so the idea is to do some sort of machine learning, although it might be a big word. So essentially is to build an approximation of the function we want to integrate. Not for any function, but for a special class of function where we know, this one we know how to do everything with it. We know how to integrate it on 1 variable, 2 variables, 3 variables. And at the end of the day, it means that we can sample directly from this distribution. And so we want to build an approximation. Maybe it's not going to be super good, but maybe it's going to be okay. And then from that, we will sample directly from this, which amounts to build a change of variable u of x, where the Jacobian is 1 over p. So now instead of f, you will have a new integral, f times the Jacobian, and the Jacobian is 1 over p. Essentially, you are integrating something which is almost flat. And if it is almost flat, then if it is flat, you can actually integrate it with 1 point. That would be the perfect case. We don't have that, but essentially the idea is to use this approximation that we are building to do the important sampling. And so this is an example. In the initial work, we did some very simple approximation. Essentially, we tried to see if we could get approximate the integrand with just a product of 1D function of the difference of time between neighboring times. So very simple class of function. Now we are using actually much more complex function. Actually, we are using matrix product states, essentially tensor train, and the results are amazingly better actually. But already with this, if you look at the integrand, this is a bare integrand that you have on log scale. So you see it's well concentrated in some part, and you have some tails, and maybe some tails on the diagonal in 2D. And after you do this transformation here, you change a variable, you get something which is almost flat. And that's much, much easier to calculate. And so so essentially the idea is to do some machine learning on a special class of functions that are nice functions in the sense that you can, this one is obvious that you can integrate on partial variables on any variable you want. This one is maybe not as obvious, but you can, and now we have developed all the apparatus to do that. And the next stage is, once you have done that, you can calculate the integral. And instead of using random numbers now, which are sort of not so good, because random numbers, they tend to, maybe you will get more numbers here, and then a big hole with no numbers there. And so they are random. So because they are random, we have this 1 over square root of n, and essentially the 1 over square root of n come from the fact that they are not very homogeneous. So you will have you will sample more regions than other. And there is nothing you can do about it. So instead of that, we will use what is known as low discrepancy sequences. So they come in many flavors. Most well-known is Sobol. Lattice rules are maybe not as well-known. It's also known as QUASI Monte Carlo. And essentially, the idea is to use now, instead of using random numbers, we use something which is as homogeneous as possible. And if it is as homogeneous as possible, then we sample the integral better, and we have a chance to get a better convergence. We can only do that if we have a way to do the important sampling, which is why the previous step was actually the most important one, how to build an approximant good enough to kill the dimensional curse. And oops. And so this is the reason. Yes?
Sorry, Xavier, since you mentioned this, I was actually, there's something I would like to understand better. So to build an approximant, you need to, first of all, sample the function. So you need to find where it is non-zero, and you need to acquire enough information to like find the transformation that stretches your, makes all the regions important. Yes. Does this not bring the dimensionality curves up again? Because you first need to find this region in space, and you need to characterize it again.
No, in practice, no, not at all. For instance, I mean, it was not clear that such a simple function would be good enough. It could be that the structure was bad, but if you believe that this is a good approximation, you can just essentially go through one variable here, and then same here, and you get directly this function by just reading your actual function there for all other points fixed. So if this is so you could get it very easily, right? Now the question is whether this is good enough. And for that, to understand that, you have to go back at the structure of the determinant and to understand how it. I mean, these Feynman diagrams essentially they have a structure which is more or less like this. Essentially, a vertex interact mostly with the nearest vertex in time, because these green functions they decay when two times become far away from each other. I used to have what I call this plasma model, where essentially you think of the times as classical charges, like with springs in between them, and you see that when you try to pull them away from each other, the integrand goes down, and you can really look at the structure and understand it. So there are some physical reasons why we believed it would work, and then we tried, and then the nice surprise is that even with this very simple ansatz, it works already surprisingly well. I'm not going to show you the new result with this tensor networks, but this is incredible. It works incredibly well. Actually, we are even considering getting rid of the Sobol or low discrepancy sequence altogether, and just taking the integral of the approximant as the approximation of the integral. And so, yeah, so let me show you this is the first plot Marjan, I forgot to acknowledge my collaborators. I will go back to that at the end. So Marjan is a student that did this machine learning things. And so before we were doing Monte Carlo sampling, and this is typically one run. This is for n equals 6 and 8, you see, in blue, as a function of the number of function calls. And you see, you get noise. And so this is the ratio of what we want divided by what what we get divided by what we want. It's a case where we have the exact result known from better ansatz. So it has to converge to 1. And you see it converges. I mean, but you need millions of points to get something reasonably good, but you know, the precision was not that big. And with the new technique, this is what you get, orange and red. So the improvement in convergence was dramatic. It was really a 2 million time improvement. And if you look at the error as a function of n again, now you see that you have 1 over n. At least in the base cases, it doesn't work always like that. But in base cases, we have 1 over n scaling instead of the 1 over square root of n, which is the dashed line. So there is at least one case where it works very, very well. And actually, in practice, what we found is that with this technique, before we started to use the matrix product approximant, which is really, really even way better. But before that, it was anywhere between 1,000 times and 1,000,000 times faster than Monte Carlo. So it was a good idea to do this, even when it didn't work well. Okay, so I'm done with. Oh, I'm running out of time. I think it's 45 minutes, right?
Can be more.
Okay, I will try to. So the last problem we have to solve is, okay, well, let's say we have calculated 10 coefficient, 15 coefficient of an expansion of something. But now what we are interested in is not in coefficient, we are interested in this something. So it's called the reconstruction of a function from its series, from a finite number of terms in this series. So let me start with a very simple example. Suppose that you have 1 over 1 plus u. Okay, that's a very simple function. Here it is. But you don't know that. You don't know that it is 1 over 1 plus u. You only have the first 10 coefficients of the expansion, which happens to be 1, minus 1, plus 1, minus 1, plus 1, minus 1. And so, of course, something you can do, you can just take the polynomial here as an approximation. And if you do that, and you truncate to 4 terms, you will get the dashed orange. And if you truncate to 5 terms, you get the green. And then 30 terms, you get this. And 31. And even if you take 1,000 term, you actually, it's going to diverge here at u equal 1. That we know because this is the radius of convergence of this series. So there is no way you can go beyond this radius of convergence. And it's annoying because it's really where you start to see something. Usually the radius of convergence corresponds to the characteristic scale, which means that you start to see something and then your series diverge, and that's extremely frustrating. On the other hand, this function is very smooth, you see. Nothing happens at u equal 1 at the radius of convergence. It diverges because at u equal minus 1, there is a pole. And we want to calculate here, and I really see morally there is no reason why I shouldn't be able to cross this point, because on the other side there is a pole at the radius of convergence. And so we want to do what is known as resummation, and I'm going to explain you a little bit how we do it. Essentially, the idea is to get rid of this pole. So we are going to do conformal transformation. So we are going to change to transform the complex plane in a real part and imaginary part of the interaction parameter in order to move this guy away and move the guys we are interested in closer. Essentially, that's going to be the idea of this reconstruction. And let me show you already just one result for an actual something that we are interested in. It's a Kondo temperature, so essentially it's the width of the Kondo screen. So if you truncate your series, in this case, it has a radius of convergence of 5. So you see this for different truncation, you see that. You see it's really, you can see that something is going to happen, and then you cannot calculate anymore. And after the reconstruction, I will get the red plot to be compared to energy. So energy, you need to do a separate calculation for each u, so you have only a few points, and to be compared with the exact better and that result that we can have. And actually, it's a nice blind test because it was a referee who told us about the better and that result, and we didn't know about it. And we had, I will show you, we had a slight discrepancy with energy, and it happens that we actually, energy was wrong, we were correct, and so on the better and that allowed us to know that the problem was not with us, but with the energy data that was not precise enough. So it's a case where you can really go all the way to u equal infinity. It's not always the case, it depends a bit on the problem, but we can reconstruct the entire things exactly, with up to some precision, which you can see here in the spread. And so for that, again, the idea is to use what I call the separation property hypothesis. And so this is my radius of convergence, which means that somewhere on this disk there is a pole or a punch cut or something, some non-analyticity. And I want to calculate here in this gray region. So the idea is to find a region here, like this region C, where there are no poles inside, and then we will make a transformation that transforms this into the unit circle. So everything inside that will go into the unit circle, and there will be no poles. Therefore, the U0 will be inside the unit circle, and it will be inside my radius of convergence, and I will be able to compute them. So the idea is to find whether there are, of course, if you have poles on the real axis, it will not work, but it will never fail blindly. It's a technique that is not guaranteed to work, but if it works, it tells you, okay, I work. You can be confident in the result. And if it doesn't, it tells you, sorry, there must be a pole somewhere in the region, and the technique is not going to work. And so, yes, so essentially we can measure this radius of convergence pretty easily. You can just look at a coefficient on how they decay with n, and the slope is essentially your radius of convergence. And you have, for instance, initially you have a series that has a radius of convergence of order 1, that would be no decaying, there's no decay or no increase. And then after this transformation, you get something that decays much faster. And that's an indication that you've done a good job. So I'm a bit out of time, so I'm going to skip some details there, but we have a way to actually locate the poles of the series. Essentially for that, we make the series for 1 over the thing, and we look at the zeros, and we can locate the poles. And then we have all kind of, and then we could check that with better on that. And then we have all kind of conformal transformation. For instance, this one is a Euler transformation. It essentially, it maps, well, color to color here. So you see the line here maps to the unit circle, and the gray to gray. And so if your pole is in the white or gray area, they will be outside of the unit circle, and you will be happy. We can also do that with parabolas. And now we have even generalization of that with Schwarz-Christoffel transformation, which means we can build pretty much any shape we want and exclude poles and do the resummation this way. And there is also some Bayesian inference, but I won't discuss them too far. Yeah. Okay, so I'm just going to finish this talk by just showing you a few data points. So these are the first benchmark we did for the spectral density. Again, you see energy compared to quantum Monte Carlo, and you see we have a very big, very nice match. It's interesting to see that the non-interacting result corresponds to this dashed line here. So even though we are doing perturbation theory, you see we can get an answer at the end of the day which is very different from the non-interacting result that you started with. Well, that's something which is, I think is very promising. It also works for the self-energy and the imaginary part of the self-energy, which are more sensitive than the spectral function itself. And it also works out of the, this one is even more striking, you see. So this we have epsilon d, so we have a voltage gate. So now the resonance that we build is at the Fermi level, and is different from the one that we started with. So I think it's nice to see that from perturbation theory, you can really not only get something thinner, or not only get the sideband, but also you can even shift totally the position of the resonance. And you can make the same thing. We can make, this is the same data, but now a color plot. Actually, color plot is a bit misleading because we have very, I would say, very strong quantitative agreement up to u equal 8 or 10. And after that, it looks well on a color plot. But if you compare with energy for u equal 12, we start to see a significant deviation. But again, this data were actually taken when we were actually using Monte Carlo sampling. So now with the new technique, I'm pretty sure we could go much farther. And you can calculate out of equilibrium, which energy can do. And actually, there is only one technique that can try to calculate, but it's a very different technique. Essentially, they are doing the expansion in power of the coupling to the lead. So it's called inchworm. So that's our competition at the moment. But it has very, very different application. I mean, okay, there is this one problem where we could try to apply it for the same problem. But they only can work at high temperature, so we had to raise temperature from T equals 0 to whatever they could reach, and also limit the bandwidth before we could do any combination, any comparison with them. So say for 0 temperature, we have no technique that I'm aware of that I can do this kind of calculation. Once again, exactly, yes, it's a controlled approximation. You have some level of accuracy, but except for that, you're doing things exactly. And we could do, for instance, we could do a sweep on this Coulomb blockade and start to see the Coulomb blockade, or how you destroy your Kondo resonance when you put a bias. And so we can really study this model in detail now. Current versus V bias. And I will stop maybe with this one. If you want about this one, it's we calculate J-lesser essentially. And at equilibrium, you have if you take the ratio between J-lesser and the imaginary part of the retarded Green function, you must find the Fermi function. So we define the non-equilibrium Fermi function as the ratio. So at equilibrium, it must be a Fermi function. Out of equilibrium, for instance, without interaction, you can get a double step out of equilibrium function. It's something that has been measured, for instance, by Hugues Potier a long time ago in copper wires. So these kind of things have been measured. And now we can actually calculate what happens to this non-equilibrium distribution when we switch on interaction. It's actually pretty funny because you still get this jump here and some linear scaling between. Okay, it's not something we have understood perfectly well, but we were pretty happy that we could start to calculate non-equilibrium objects like this. And so it's already a bunch of new things we could look at with this technique, and we have not even started to look at. And with this, I will stop. So it was a technical work, a technical talk about this attempt to try to bring in correlations in nanoelectronics, essentially in quantum nanoelectronics. It's working way better than I have anticipated initially, and now we have new techniques for these things. And it seems that so we are attacking now lattice problem, like some sort of so when we have the interaction on many sites, not just one, and we have reasons to believe that it will work very well. And you could use this for all kinds of problems. Even I think even order 2 or order 4 perturbation theory would be interesting for many cases. But it seems that we can go much further than that and even get to non-perturbative results. And so that's something I'm very excited about, and I hope we have some nice breakthrough coming up soon. So with this, I stop. Thanks a lot for your attention. If you are interested in the details, you essentially everything is in these 4 papers. Thanks. And if you have some questions, I think now is a good time. Please.
Thanks, Xavier. Very interesting stuff. So I was wondering about the limitations of the current approach. Do I understand correctly that that the complexity is exponential in the number of interacting degrees of freedom? Is that right?
Yes, it's 2. The complexity is 2 to the power, the order to which you want to calculate. And so 2 to the 10 is 1,000. So typically,
I know, but like this is like with a single site interaction. If you had an interaction of 5 sites that are all to all, then you would have more, right? Or is that not the case? No,
on paper it doesn't scale with that. And we have done some preliminary result on the 9 interacting sites, so 3 by 3. So it was a 2D plane with 9 interacting sites, but it was a long time ago before we understood many things. There was some sign problem, so the integral was quite oscillatory. And because of that, we could only calculate maybe 7 terms instead of 12. But we got the 7 terms all right. And now we are going back to this with much better techniques. And I'm deadly sure that we will be able to calculate into the so the exponential cost is with order. That's the only limitation is order.
Mm-hmm. All right. So if I may, I had also another related question. So your starting point here is purely non-interacting.
Yes.
So I'm wondering if it would be possible to choose as a starting point some kind of mean field or a self-consistent mean field and only treat perturbatively corrections on top of mean field.
Yes, it's possible, and we have started to play a little bit with that. And the gain is usually you can actually get a much larger convergence radius, which means that you can go larger in the. So yes, there are ideas like that. Also, people. So I didn't talk about the competition. We don't have competition for real time, so for transport or out of equilibrium things. But there is many groups. I mean, not many, but quite a few very strong groups doing imaginary time dramatic approach. They also have played with these counter terms, and you can try to do RPA also if you decouple with the boson. So there are all kinds of games we can play to get a better, either a better behaved series, or maybe you can start from something which is already close to what you want, and then perturbation will do very little. And so all kinds of ideas like that can be tried. And we sort of tried them for simple things, and it seems to work. Yes, it seems to work quite well.
Thanks.
Hi, Xavier. Can I ask?
Hi, sure.
Yeah. So you mentioned on several occasions this competition. So like there are even open source codes now available to do KELDYSH diagrammatics in time, such as this package called NESSI, and they can do even DMFT. But the main
this is very different. Yes.
I know. It's a KELDYSH diagrammatics, but the main advantage of what you have is actually you have the leads, and these guys do not have the leads.
Also, I don't think they can go to order 15. I think they go to order 5 max.
Well, yeah, they actually they don't really go like this is another topic, you know. Is it good to cherry pick diagrams? Because most of these people would cherry pick diagrams and do like GW in time or like.
Oh, that's okay. That's something. So we don't cherry pick. We just take all of them. Yeah.
Yeah, and that's actually conceptually very dangerous, because in mathematical sense you can only reshuffle diagrams if you have a absolutely convergent series, but none of the series in physics is of that kind. So in fact, some of the testing by this diagrammatic Monte Carlo community in equilibrium shows that it is better to do what you do, which is just every diagram at order 1 and 2, then let's say cherry pick a diagram and then do self-consistent.
Yeah, but there are some interesting things that can be done, but I agree, if you want to go into correlated regimes, you want to have a systematic approach. You don't want to...
Yeah, so the question, like, so there are these guys in Nessie, there is Bonitz, he now has very powerful, efficient algorithms. He even claims he got linear scaling on Haber clusters, but again, he doesn't have the leads. So he can do like a big Hubbard systems exposed to time-dependent perturbations, but without the leads, you don't have the continuous energy spectrum. And without continuous energy spectrum, you don't have a good mechanisms to dissipate, bring steady state and stuff like that. So now the question that I was wondering about, is there anybody else who has efficiently been able to attach the leads to, let's say, the same systems? In other words, like, have you ever seen TDMRG people being able to attach the leads? Because, for example, Bonitz checks his calculations in 1D against TDMRG, and he can see how good are his self-energies, because TDMRG is basically exact. But the
so DMRG, I think, what people look, they take a big system and then they look at the transient.
Yeah, they look at the transient. Yeah, and I use TDMRG, but the limitation is that, again, I can do a very long chains and do like, you know, inject the current pulse, but again, I don't have the leads and I don't have the continuous energy spectrum.
So if you want that, you need to switch to what we are doing.
No, of course, yeah, your solution is the ultimate. The issue is simply, like right now, you have these beautiful examples when you have checked your results against, you know, energy and beta ansatz and that kind of stuff. So is that the only thing that you can compare to? That's my question, basically.
So it's moving very, very fast now, and I didn't show the latest stuff, but once again, we have this new approximant, where we use a tensor train, so essentially matrix product state, but not for, very different from DMRG. Now we are using tensor train for the integrand. So not for an object, a wave function very, very close to the Hilbert space and so on. Here we are taking essentially, if you think about, you want to integrate a function of 10 variables, well, think of it as a tensor with 10 indices. And then you want to approximate that with a matrix product state. And so we are doing these kind of things. It works like magic. Honestly, I'm afraid, I'm amazed by the result. And so now we are moving to Hubbard models and kind of things like that. And very soon I will be able to show you some data for, I would say, I think a large class of system. But okay, I don't have the data yet, but I have a strong indication that it will work. Let me, before we go on, I forgot to mention my collaborators on this very, very bad idea. So just want to say that most of what I said has been done by 2 PhD students, Corentin, Bertrand, and Marjan Maček. So Marjan for the machine learning aspect, and Corentin actually was the one to do this nice splitting of the spectral function. Recently also, Philipp Dumitrescu is a postdoc in New York with Olivier Parcollet, so in the Simons Foundation. So he's been also working a lot on this. And my senior collaborators on this are Olivier Parcollet, so I've been collaborating on this since the beginning with him. He's in Simons Foundation in New York. Bill Triggs is a machine learning guy that told us a lot about machine learning, and it was very interesting. And Serge Florence did the energy stuff we compared. Sorry,
can you go back to that slide when you compare it to the only competition, which is Emmanuel Gould and his team?
Inchworm, yes.
Inchworm, yeah.
I think we have a better one now. I couldn't put.
No, I mean your curves look so much neater and sharper than what they have. I'm just
also they had I think 1,000 times more computing hours on them. I mean,
1,000 times more what?
Computing hours. CPU.
Oh, you mean like computation complexity?
They had to use a huge, like they went to huge computers and spend a lot of hours to get this curve.
But they are trying the same problem. One single Hubbard site between two 1D leaves.
But very different expansion. So what they do is really they are expanding in power of the hopping to the leads.
Yeah, I know. What they do, they solve. That's called hybridization expansion. They are kind of solving the middle part exactly.
Yes. So which means that there is no chance they can do Hubbard with it because they are exponential in the number of interacting sites. While we don't care about the number of interacting sites. So it's very different way of doing the expansion. And that's why actually I didn't even consider taking the direction they took, because I really want to have I'm more interested in weak interaction on a large system than just studying the quantum dot. So Inchworm is very good for DMFT kind of problems, I guess, even though they have troubles to go to 2 orbitals or 3 orbitals, which are the interesting things to do now. So it's different, it's complementary, essentially. We are doing it power of u, they are essentially doing it power of 1 over u.
I would say what they do is more like improving quantum master equations, because people who used to do quantum master equations would stop that expansion in hopping to 4th order.
No, it's much better than that. I mean, they get the Kondo peak, they get the Kondo peak, they get the Kondo temperature. Okay, so it's much better than just.
But the key issue is that what these guys were claiming is that with this hybridization expansion, you could go to very large U. So can you actually go also to very large U and get better results from whatever they can get?
No, I mean at some point I'm limited in U. I mean. Here you see I can go to U equal 15 or 16, but if I actually show you the data, it will look bad. I can only make color plot at this kind of IU. So if I want to go to very IU, I need more precision. So this is my limitation. And
more precision in what? In
the coefficients, in the calculation of each of the coefficients.
Okay, so it is not more diagrams, but more precision in each order.
Yes. Yes, usually you need, once you get 15 diagrams, I mean, you need enough diagrams to be in the asymptotic regime. And okay, technicalities, if you have one pole which is hiding another pole, then maybe we will need a bit more diagrams too. It depends a bit on the structure of in the complex plane. But in practice, really, you are whenever, I mean, if you want to go to IU, you are burning precision. And so, but again, this calculation has been done with 1 over square root of n scaling, and now we have better than 1 over n scaling for the so now we can get 5 digits, 6 digits. Here we had 1% precision. Now we can get 5 digits. So I'm pretty sure that if we do this calculation now, we will be able to go to essentially any U we want for this problem. But yes, essentially they have trouble going to small U. We have trouble going to IU. It's different technique, different limitations. But you see, already everything has happened here. And then it just get thinner.
Well, the real advantage is to really move to something extended, because, you know, one side is the academic problem.
That's the next stage. We need to demonstrate that we can do an extended problem, and that's really what we are doing. I mean, we will be doing that in a week or two. I mean, we are. Okay, it's a highly technical. Thing. I mean, you have a lot of technical problems to solve one after the other, and now we are in much better stage than we were like even 6 months ago. So now we will move to this 2D problems.
Thanks.
No more questions? Well, if not, thank you guys for...
Thanks, Xavier. Good luck with